Enzyme kinetics is the study of how enzymes bind to substrates and convert them into products. It helps us understand the rate of enzymatic reactions and the factors affecting them. Two different equations are commonly used in enzyme kinetics to describe the rate of enzymatic reactions. The first is the Michaelis-Menten kinetic equation, and the second is the Briggs-Haldane kinetic equation. These two equations are obtained using two different assumptions. The Michaelis-Menten equation is derived using the rapid equilibrium assumption, whereas the Briggs-Haldane equation is derived using the steady-state assumption. First, let us derive the equation for one substrate, one product reaction using rapid equilibrium assumption. This equation is derived by Leonore Michaelis and Maud Menten in 1913. At that time, the three-dimensional structure of proteins was still unknown. The first 3D structure of protein, namely myoglobin, was not published until 1958. Thus, at that time, it was unknown whether an enzyme actually possessed a defined active site. But first, let us consider the general approach used to derive any equation in chemistry and physics using analogy. The first rule to remember is to convert non-measurable quantities into measurable parameters. Consider the factors that make women happy as an example. One may write that the factors involved in women's happiness include health, wealth, beauty, and love. Obviously, a woman's health can be quantified using measurable parameters such as height, weight, blood pressure, etc. Similarly, a woman's wealth can be quantified using parameters such as material possessions and bank deposits. Thus, in this case, health and wealth are considered measurable parameters. Love and beauty, however, cannot be easily measured. For example, one often hears the saying that beauty is in the eye of the beholder. Although beauty is subjective, one may scientifically attempt to describe it as being dependent on factors such as height, eye size, skin complexion, and weight. Next, substitute this expression into the equation above. The remaining parameter is love. If love can be expressed as a measurable parameter, then a sound scientific equation can be obtained. Rule number 2 is to attempt to rearrange the equation into the form y equals mx plus a, if possible. The Michaelis-Menten equation derived is v equals s multiplied by v max, divided by km plus s, produces a nonlinear curve when velocity is plotted against substrate concentration. A nonlinear curve is undesirable because it is less predictable and requires more data points to be accurately drawn. Therefore, Lineweaver-Burke later rearranges this equation into the following as shown. When compared to the general equation y equals mx plus a, y is equal to 1 over v, x is equal to 1 over s, the slope m is equal to km over v max, and the intercept a is equal to 1 over v max. This equation produces a linear curve or a straight line when 1 over v is plotted against 1 over s. In this plot, the intercept on y-axis is simply equal to 1 over v max. Now, back to the derivation of the Michaelis-Menten equation using rapid equilibrium assumption. This mechanism involves 3 steps. First is K1, the rate constant for the encounter between E and S, which depends on the concentration of S and E, temperature, and other factors. Obviously, the higher the concentration of E or S in the reaction mixture, the higher the rate of encounter between E and S. Second is K minus 1, which is the rate constant for the dissociation of S from the ES complex, and therefore depends on concentration of ES. Third is K2, which is the catalytic step, also known as Kcat, representing how fast S is transformed into product by the enzyme. Therefore, the rate or velocity of product formation is written as follows. To derive the rate or velocity equation, consider the following. Assume that a given number of cars start at point O and want to travel to point X. What is the rate or velocity at which the cars arrive at point X? To To go from point O to point X, the cars must pass through Chestnut Street, North Broad Street, Penn Square, and the 15th Street. Now, at what rate do the cars arrive at point X? According to the bottleneck assumption, the overall rate of a process is determined by its slowest step. In this diagram, the number of cars at different locations is labeled A, B, C, D, and E. The flow of cars on each street is controlled by the traffic light at each intersection as shown. Assume that the traffic light on the North Broad Street remains red for most of the time compared with the other traffic lights, and therefore is the slowest step. Therefore, the rate of cars arriving at point X equals the number of cars, B, multiplied by the rate at which the traffic light at North Broad Street turns green. Now let us go back to the previous enzymatic reaction. K1 and K-1 are physical steps involving substrate binding to the enzyme and dissociation from the complex. Physical steps generally occur at a faster rate than chemical steps. K2, on the other hand, is a chemical step involving the breaking and making of chemical bonds. This step generally proceeds at a slower rate than physical steps. For example, cleavage of a peptide bond by a protease involves breaking the peptide bond and forming new bonds. Thus, if the catalytic step occurs much more slowly than K1 and K-1, then K2 can be assumed to be rate limiting. Therefore, the reaction rate equals K2 times the concentration of the enzyme, substrate complex. Next, the rate of an enzymatic reaction depends on the amount of enzyme used per reaction. As enzyme concentration increases, the reaction velocity increases accordingly. Therefore, one must take this into account by dividing the reaction velocity by the total enzyme concentration used in the reaction to obtain the equation shown. The total enzyme concentration in the reaction can be expressed as the sum of the free enzyme and the ES complex, as follows. This derived equation would be perfectly adequate if the concentration of the ES complex were known. The concentrations of enzyme and substrate are known from the amounts added to the reaction mixture. However, the amount of enzyme substrate complex formed in the reaction is unknown and cannot be measured directly. Thus, the concentration of the ES complex in the equation is an unknown quantity. The Michaelis-Menten model uses the rapid equilibrium assumption to express the unknown concentration of ES complex in terms of measurable quantities. When K2 is much smaller than K1 and K-1, it can be considered negligibly small and may be ignored. One can then use the rapid equilibrium assumption, which assumes that after their addition to the reaction mixture, equilibrium between E and S and the ES complex is established rapidly. One then obtained the following equation for Km. Note that under this assumption, Km represents the dissociation constant for substrate binding to the enzyme. This equation can be rearranged as the following. Next, substitute the expression for the ES complex into the equation above. Next, the equation can be simplified by canceling all terms that contain free enzyme on the right side of equation. Then multiply the numerator and denominator on the right-hand side of the equation by Km. Now, move ET from the left-hand side of the equation to the right-hand side. Vmax represents the maximum velocity achievable in a given enzymatic reaction. Vmax is limited by the total amount of enzyme available in the reaction and by the rate, K2, at which the enzyme can convert substrate into product at the active site. Depending on their catalytic efficiency, each enzyme has its own unique catalytic constant. For example, in theory, DNA polymerase from a dog will have a defined cat value, and DNA polymerase from a cat will have its own distinct cat value. Next, substitute ET times K2 with Vmax. The final equation obtained is known as the Michaelis-Menten equation. In this equation, S represents the substrate concentration used in the reaction, which is a known parameter. Km and Vmax are the parameters to be determined from the plot of substrate concentration versus reaction velocity. The plot of substrate concentration versus reaction velocity is shown here. When the substrate concentration is gradually increased in the reaction velocity increases accordingly, but eventually reaches a maximum at the plateau. At the plateau, all of the enzyme's active sites are saturated with substrate. Therefore, a further increase in velocity is not possible. Thus, the reaction reaches its maximum velocity, or Vmax.